Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Today we're going to be fussing with lighting, seeing what we can do. We're trying to sort of push forwards into getting some lighting into the game. We're just not sure what that lighting is going to be like. Because lighting is very difficult to do correctly, and in our case it's impossible to do correctly because we don't even have 3D models because we are a 2D game. But we are trying to play around with lighting to see what we can do that will produce an interesting or useful effect for us. One of the things that we have been doing is writing shaders lately, and one of the things one thing that kind of confounds us. I'm going to load up the code base here so you can see what I'm talking about. Is that I didn't really make any system for loading the shaders from disk. Largely because I don't like shipping extra files with a game. So to be honest, I kind of like them being embedded in the executable. And so if we were going to do something like loadable shaders, I would probably do it, honestly, I'd probably do it through the hot code reloading system, which is probably something we should do eventually anyway. Since the hot code reloading system kind of handles this case as well. We just didn't happen to put the renderer in the hot loaded section. We should, right? But all that aside, one of the things that's been confounding us, since we haven't really had much of a need to hot load the shaders at the moment, because the game boots very quickly, so it's not really that big of a deal. But one of the problems we've been having is because we just put them in as strings in our executable, is the indentation's all messed up. Because once we open something as a string, we end up in a position where the for-coder, when it looks at what we've given it, thinks that we are talking about just a giant group of characters, and it smushes all the indentation out of our shader code, which makes it hard to read. Simple ones like this aren't so bad, but you know, when you get into ones that are a little more complicated, which we have a couple now that are somewhat complicated, you know, you look at something like this, and it's hard to read. It's difficult to read some of the slightly more complicated shaders. Now, I was like, well, I wish I could fix that, but I can't think of a way how to fix it. I tried a little bit, but I couldn't do it. Martins, who many of you already know, he answers all the questions on Handmade Network. Like all the questions. He seems to know everything. Figured out a fix for this that may work, so let's try it. What he suggested was, since we're using an arbitrary string opener here, apparently the rules of C++11 are that if we open a string with one of these sort of like, what's the word I'm looking for? With one of these like arbitrary modifiers, that arbitrary modifier is allowed to include a closing quote, apparently. So we can, in theory, do this, and then at the end of it, we can do that, right? So the question was, if we did that, would for-coder no longer think it was a long string? Unfortunately, it looks like here for-coder is too smart for us. It looks like for-coder knows about that string syntax, and so as a result here it looks like there's no way to turn it off. So, because like you can see I've got the closing quote here, but unfortunately all of this remains a string, according to for-coder. So yeah, it looks like for-coder is just a bit too smart. It understands how to do open and closed strings like that, so that's too bad. I guess one thing that would be really cool if for-coder did is like if you could say in here like that as the string open and closer or something like this. You know, like something that would tell it to indent the string in a normal fashion. Like that. And so for-coder would know you know, if you made a string like that to allow indentation inside it because it was supposed to be C code or something similar to C code that could be indented that way correctly. So that would be cool. Let me see. Blah blah foo. Let's see. For some reason, 4coder has a maximum length here. Is that also part of C? Meaning, is this not considered one of those strings anymore? Because that would do it. Oh man, 4coder got... Did 4coder die? No, it didn't. Okay. Nope. So I guess that's just part of C as well. So you can't have longer sequences. 4coder's just telling you that. And parsing that properly. So yeah, I don't think there's any real way around it. Yeah, I don't think there's any way around it, unfortunately. So there you go. Thank you, Martins, for trying. That was a really good idea. Unfortunately, 4coder's a little too smart for its own good in this case. And so basically, we will just have to ask Alan. I think we'll just have to ask Alan to fix it for us. I don't think there's anything we can do at this point. We've tried pretty much everything we can think of. All right, anyway, let's go back to game programming here, and specifically rendering programming. Now, where we last left off, we sort of had the ability to take a look at several buffers that we were storing with information in them regarding the lighting. And one of the weird things that we sort of have here, right, like you can see what's going on here. We've got like our subsampled lighting buffer here, and we've got our normals here, and we've got the emission, current emission blur thing happening here, and blah, blah, blah. Excuse me. So one of the things that I had been doing is we were sort of playing around with the lighting in this setup that we've got here. And it occurred to me as we were doing this, and I thought about it this week, I think I kind of realized that we've been taking a slightly inaccurate approach, or rather a slightly unproductive approach here. And what I realized was, excuse me, what I realized was we are sort of making things a lot harder on ourselves here, because what we're doing is we're trying to develop the lighting algorithm in like the most unfavorable circumstances possible. We're trying to develop a new algorithm because we don't really have any existing algorithm we're implementing directly. We're trying to implement a new algorithm in like the GPU directly, and we don't even have the ability to debug this GPU. We can't use like a GPU debugger on it because it doesn't work with a GPU this old. And so it occurred to me, it's like, how are we ever going to figure it out, right? It's like the most unfavorable way to possibly develop something. We can't even see really what's going on. It's laborious to store information because we have to create like new textures to put the data in and all this other stuff. It's just really inconvenient and bad. And so what I realized is, why don't we not develop it that way? Instead of doing that, why don't we just write the lighting on the CPU side, right? Like, what if we just wrote the lighting on the CPU side, finished it, and then ported it to the GPU? Right? It seems like a pretty easy approach to me that would be a lot more fruitful, because what we could do is, like, for example, if we want to do this thing with reflectors like I was trying, we can just create a struct for the reflectors, create as many reflectors as we want, run the lighting on the CPU side, and then download the results to the GPU and draw the lit scene with that. And that way we can even draw those reflectors, so we can actually like send down reflectors as geometry to see what their current status is and all that other sorts of things, right? So it seems to me like maybe that's a smarter way to go, because if we did that, then we wouldn't have to worry about all the GPU side stuff that is endemic in trying to implement a complex algorithm using nothing but pixel and fragment shaders, vertex and fragment shaders, because then it's more like just writing like a compute shader basically, and then once we have figured out what we want to do, then we can translate it, right, down to something that the card can do. So that's my thought. And so I was thinking of trying that this weekend. That way we can sort of get out of the business of trying to do this on the hardware side of things, which to me seems very difficult. All right. So what I was kind of thinking about there is just literally trying to do some of the stuff with the reflectors like on the C side, right? So inside the render group, right, we've got this thing called render entry textured quads, and render entry textured quads just outputs all of the, basically substantially everything in our game. It outputs a series of quadrilaterals. Each quadrilateral is, either going to be a sprite or the side of one of our like structural cubes that we use to make up the ground for the look of the game. And if we want to, we can easily grab one of these textured quad elements, and we can loop over all of the quads on the CPU side. So what I was thinking we could do is just take all of those quads and generate reflectors for each one on the CPU side, compute lighting between the reflectors, and then render those reflectors to see what the lighting actually is, right? And furthermore, we have a way of doing this in a really convenient fashion. Because we can hijack all of the textures and colors in the quads at any point in the pipeline, what I can do is just insert effectively I can sort of insert a piece of code that just hijacks it, does the lighting, and outputs the lighting directly to the quads. And I think that will pretty much solve our problem for us, I think, in terms of development. So let's just take a look at this and see. So here in the Peel Composite program, you can see that we've if'd zeroed out the lighting. So there is no lighting going on anymore. And that's why when you run the game at the moment, you can see that we sort of have an unlit world. But otherwise, it's rendering as we normally would expect it to render. Now, if I want to insert that hijacking, what I can do is say, okay, inside world mode, there should be a time when we actually push the rendering out here. You can see at the end depth peel state of things, for example. So what I want to do is basically hijack the render group here. So I'm just going to insert a thing called lighting test into render group. What I want to do here is I want to create something inside the render group at the end that's a dummy function. Well, it doesn't have to be inline. So after we have pushed this render element to end the depth peels, we now know that right behind our current render element is one of these on the render stack is going to be one of these texture quad sets. So what I can do is I know that I can just loop through the the render stack, looking for these right now and do lighting on them. So what I can do is grab out of the render group, right? Because the render group itself, excuse me, because the render group itself, at least I believe, let's see, that's not in here, so that's going to actually be in here. The render group has a current quads one. Oh, and in fact, I suppose we could just do it that way. Maybe I want to do this before then. Maybe I want to do it on current quads. So maybe I want to say this. So what I want to do here is say, let's do that right before we push in that case. So let's put it here. That way the quads will be correct as written. So what I'm going to do here is I'm going to go into those textured quads. And let's see here. So I don't know what the easiest way to get the pointers to things is going to be. I think, yeah. So basically we just have quad count and vertex array offset. So basically what I'm going to have to do here is I'm going to have to grab out the pointers to where the information is for the textured quad. But that's not a big deal, right? We've done this before. You can see here on push quad, this is how we were writing to it in the first place. You can see how we get the vertex array there, and you can see how we get the quad bitmaps. So I can just kind of come down here and do that. So what I could do is this. I can say, here's the quad bitmaps for vertex array offset. And that should give me pointers into the render buffers for the vertices and the bitmaps in question. So this is really all we need, I think. So once I have that, I can loop through all of the quads that there are, right? I can say quad index, goes up to the quad count. And inside this loop, I can access the vertices and the bitmaps. What I want to do is basically nuke out the bitmaps. So what I can do here is say like bitmaps quad index equals that white bitmap. So now there will be no sprites. There will just be flat, pure white textures, right? And if I want to here, I can say, I can pull that commands out because I'm going to need it. I think it's called group commands. Is that right? Yes. And let's take a look here. So lighting test, I can't put a loaded bitmap, just a double star. There we go. And so now all I need to do is call this before ending the depth peel, which is what I was doing now, and it should go through and be able to access all this information. So just to start testing it, like I said, this will nuke everything and just produce white, right? Well, not white, whatever the color is of the thing. And you can see that's exactly what it did, right? So here's all of our sprites, all of our quote unquote reflectors, and this is exactly what I wanted, right? So that's good. And similarly, if I want to, I can edit the vertices. So I can do something like verts plus equals 4. I could do this even. Oops. So now I know that on every quad that's sort of lined up, if you will. Now if I want to edit the quad, or access the quad, which is exactly what I want to do, I can pull out each individual vertex of the quad the same way that I did it when I was pushing them on. So I can know where each of these quads is by, again, just doing this sort of a process. So if I want to, I can take the textured vertex pointer here and say, all right, let's say that I've got each of these separately. So let's say I do something like this. So I can access each one of the vertices of this constituent quad through a convenient name, v0, v1, v2, v3. And similarly, if I go look, you know, I've got this struct about the vertex there, textured vertex, and you can see we've got a position, a normal, a UV, and a color. Now we don't really care about the UV, but we do care about the other three values. What I can do here, is demonstrate as well that these are editable by changing everything to white. So now we should get a completely whitewashed screen. There we go. So there's our completely edited version. All right, so that gives us our sort of information that we wanted for our lighting test here. We now know an easy way to sort of get into the CPU all of the information about all of the reflectors in the scene and where they are, what their color is, what their normal is, etc. And furthermore, we can now output a lighting solution that we can look at and debug quickly by just changing the vertex colors of the sprite geometry to reflect whatever the lighting system says, right? So let's go ahead and do that. Let's start down that path. I need some tissues here. Allergy-ish. All right. So the question is, how do we want to create some space for this here? Not probably super difficult because we can just create a dummy buffer that's however big we need it to be and let that do its thing. So for example, we know how many quads are going to be here because, you know, again, this is not really something that we're going to be using long term. So I'm just going to create a dummy buffer that we can use to do whatever we want to do. And so if I go take a look in that lighting test function, let me just go ahead and set a breakpoint there rather than trying to get to it in the debugger. If we actually just look to see what is going to be, let's jump through here, 2200, 2182, 21. So, you know, if we created a buffer of 4096 things, that's more things than we're ever going to have during our testing here. So if I want to, I can just create a little thing called, you know, reflector, or maybe I'll call it a lighting element. I don't know. Who knows? But this lighting element is going to be something we can play with. And like I said, for right now, let's stick with the thing we were doing before, which is, let's just say it's got a position, it's got a direction, it's got a color, and it has a radius. So how, you know, big the thing was. So we'll leave it like that. And so in this case, we've got sort of these two notions of color like we typically do, which is always a little bit confusing, right? There's two kinds of color. There's emitted color, like I am shining color out, and there's reflected color, and they're different things. So I'll put those two in here again, and I'll do the front and back like we had. So this is now just what we were building inside the GPU. I'm just building it outside the GPU now. And again, this is because I want a way of looking at this that doesn't involve so much laborious work just to try things, because I feel like we're never going to converge on a solution if we have to try them in an environment that's as so slow as what we were working with. We did a bunch of work to get it to the point where we can do a bunch of stuff with it, but just trying to figure out what the right things to store is and the right ways to process them just seemed way too difficult without being able to debug or draw or do anything really interesting. And so I think this is just a lot more effective as a way of getting to a solution. And then we just move it to the GPU when we're done. And that part's not so difficult at that point because we're only trying to do one thing. All right. So if you imagine here that we sort of just have a set of these reflectors that are going to be generated based on the sprites and the quads that we see. I really should not be scratching my eye like this. Just, don't do this at home, folks. That was a bad idea. You may have allergies like I do, but don't scratch your eye. It only damages the eye. Actually, I don't know we know that. I think it's currently hypothesized that it damages the eye. Anyway, moving on. So what I can do here is have basically two loops, one that extracts into the lighting elements and one that pushes back into the lighting elements. So what I'll do is I'll just create a global array first that's like, the root sort of set of elements. And what I'll do is, excuse me, make two passes through. This is going to stay sort of as a thing that copy lighting out and copy lighting in. So first we'll go through and do an extraction. We don't need the bitmaps to do the extraction, we just need the vertices, so we'll ignore the bitmaps for now. And the way that we'll do the extraction here is we'll basically, we'll take sort of a span. So we'll assume V0, V1, V2. We'll assume that V0 to V2 is the span across the sprite. Again, this is just approximate for now. We can work on better ones later, but we just need the basics for now. Which is to say, for any quadrilateral, I could approximate what it's doing by saying, all right, if I was to take this, then if I want something that's as big as the, I can either inscribe something here, or I can, sort of make it bigger, as big as the whole thing. I'm going to err on the side of making it bigger for now. So what I was thinking is basically taking V0 to V2, right, if we assume that it looks roughly like this. Just taking this span and saying the midpoint will be the center, and the distance out to one of the sides, or rather the whole thing will be the diameter. This out to one of the sides will be the radius, right? So when I do this, I've got the vertices coming in here. I only need two of them. And what I can do is say V0p, V2p. If I subtract these two from each other, that's going to be V3 actually. Actually, it's probably going to be a V4 because I think they're four-dimensional because they've got that Z bias built in. That would give me the span. Now I think about it, that Z bias is actually something we want to take into account as well. We probably want things to be reflected as if they are standing up the way that we fake them to be. Yeah, so maybe we want to do it this way. So maybe we want to create V0p as V0xyz, and then we want V0p.z to plus equal V0w. something like this. That's true. All true, my friends. There we go. Cannot convert. There we go. So let's see. Okay. So this right here would give us the span. So now if I want to create a lighting element, let's just go ahead and pretend that I have one here. So here's my element. And that's just going to line up with the quads exactly. So as I spin through all of these elements, I'm going to add the quad index here and get the elements out. So then what I'll say is my element's position is going to be the span vector here. What I want to do is take my V0p and add half the span, right? Because that walks me up to that midpoint, which is the location that I wanted. So I can take that element P and I can go up half the span and get the location, center it there. Once I've got that element P, what I can do is I can create the normal from it by just looking at any one of these normals. So I believe all I have to do there is just grab one of them, because these are all flat. So just grabbing one, I don't even have to average them or anything. I can just assume that they all have the same normal, because that's basically how we've been doing it so far. If that changed in the future, I'd need to use something a little bit more complicated. The emission part, I don't really have any way of setting any of the emissions at the moment. So we'll go ahead and eliminate those. And then what I'm going to do here is just look at the reflected color. That reflected color is just going to be the color of one of the vertices. Doesn't matter which one at the moment, because again, we don't really vary the color across the vertices just yet. So we don't have to worry too much about that. But what I need to do is up convert it here. So I was hoping we had one of these, like an RGB unpack, but I don't know if we do. Let's see, RGB unpack 4x8. So that is going to pull out those RGBs exactly the way we want. So I'll pull that out there, and that'll give, yeah, the red, the green, the blue, and the alpha correctly. So that's what we wanted. And then the radius in this case is going to be half the span length, right? So if we take the length of that span, that'll give us the radius. Well, that'll give us the diameter, and then we divide by 2, and that'll give us the radius. And again, that's just a simple construction based on this. We take this span vector, v2 minus v0, we walk halfway in the middle to get here, and then the radius, of course, is just going to be, this is the diameter, so we take the length of that span vector, divide it by 2, and we get what we wanted. All right, so let me just go ahead and create a dummy emission there. I don't know why we set this as a V4. It's not. And honestly, it's not really a ref. The ref C is not relevant either, because we're not going to remember alpha at the moment. Maybe in the future we'll take advantage of alpha. That would be like translucency, right? So yeah, maybe we'll put that in here. Maybe we'll say transparency in case we do want it. I'm going to put this up here, and then I'm going to grab that out from it. That way, if we do change our mind about how that's averaged or anything else, we can change it in a central location. All right, so let's see here. C is not a member of textured vertex. What is it called? It's just called color. So that's us getting our lighting in. So now if I run it, we shouldn't see any difference. It's just copying it into that array, not actually modifying it all. Then when we do copy lighting out, you can see here that we've got our test stuff running. What I want to do here is have some way of viewing what we actually created here. Because again, we could have a bug in this copy lighting in that would create reflectors that don't accurately reflect the world. So what I'd rather do, rather than leave everything unadulterated, I would rather go ahead and reconstruct now the 4 vertices from our original lighting data that we created, so that way we can be sure of what we're actually getting, right? So what I'm going to do here is recreate these 4 vertices from the lighting data. So let's take a look here. Here is the lighting element, which we've pulled out for this particular quad, and we're going to copy the lighting element data back into the quad. Okay. So the first thing we can do is we can say that it's got it's got that reflected color value. What's interesting about this is like we need some place at this point to put the lighting. So I guess we've got the front emit C. The front emit C is what the lighting actually is. So I guess for now what we would say is maybe we'll do like, note KC compute lighting. So maybe in here we actually go through all of our lighting elements and just copy the front, the ref C, the reflected color into the front emit C, right? So this is as if we were pretending we were doing some kind of lighting that we're not really doing, right? All right, so now when we do our copy lighting out, we know that all of the colors are going to be whatever the emit color is. So those are all going to be set this way. And so we've got a front emit here that's just going to be our pack RGB. We do have a pack, don't we? We've got an unpack RGB pack. That's what we want. So here we'll pack the front emit from the lighting element. We'll pack it back in. What is it? Is it front emit C? Yeah. And so what we need to reconstruct here is stuff like the normal and the position, and the UVs we didn't touch, so we don't need to reconstruct those, and because those aren't relevant to the lighting. So really what we need to do is use the element P and the element N here. Now the vertices can all take on the element, the normal, in this case. Although one thing I point out is the normal, if we're computing the lighting, we won't be able to see whether the normal is right or wrong in any particular way. We would have to draw it. So it's really sort of irrelevant to copy in here, so I think I'll probably skip it. Although, well, you know what? I won't skip it because we can look at like a normal map in the renderer, right, to see if it's roughly correct. So maybe I'll leave it for now. Sorry. So if you have the vertex normals here, again, they're just copying out whatever the lighting element had in it, like so. And so we've got the colors here, we've got the normal here, and all we really need to do that's any work at all really is we've got to come up with the positions. So we need to come up with our 3 different positions. Obviously, each of them, 4 different positions. Each of them is going to be based off element P, which is sort of the center of this lighting element. And we know we have a radius, so what we can do here is essentially take our sprite and the normal to that, and we can go ahead and blow out, make it sort of a diamond shape or something, roughly that size. Whatever the size that normal is, right? So we need two things. We need an x and a y axis in this case. And then when we do v0, v1, v2, v3, we can sort of create those by doing something smart here. So for example, we can do a plus x, or rather, let's start with a minus x. No, let's start with minuses. We'll start with a plus x. And again, what I'm trying to do here is just draw something out. So let's suppose that we've got the element p is here, right? We know that we have a radius, and we know that we have a normal. So what I know about this, if I want to recreate something that sort of shows an approximate space filling here with a quad, is I'm just going to be drawing something that looks like this, right, inside the circle. What I can do is say, all right, I know the radius part, which is how far it is out here. So all I really need to know is what are the x and y axes of this circle. Because if I knew what those were, I could just draw plus x-axis, plus y-axis, minus x-axis, minus y-axis, and get the corners of my sprite. Now, the reason I can't do that is because the normal just tells me the other axis. That tells me like the z-axis effectively, right? If I were to look at this on a plane, sitting in a plane, where I'm saying, here's my y-axis, here's my x-axis, and I'm trying to draw something in that plane, the normal is this, right? The normal is the z-axis. It's the axis we don't want to draw along. So how do I produce these other two axes? Well, in this case, I can use, again, the cross product to produce some of these for me, since I know that all of the vectors, x and y, that I might want. And remember, I don't care which I have. Since it's a circle, I don't care what axes you give me. Give me any axes, doesn't matter, as long as they're both perpendicular to n. Well, we know that the cross product, like we talked about before, gives us vectors perpendicular to other vectors. So if we want to, if we just had some other vector, we could cross it with n, and we would know that the result would be perpendicular to n, right? We know that that's true. So I just need some other vector. If I had any other vector at all, it doesn't matter what it is, I would get one that would be in this plane. And it turns out I could do this relatively easily, right? Why is my... There we go. So it turns out I can do this rather easily because actually, since any vector will do, I can just find a vector that is not pointing too close to the direction of n, cross it, and get a new vector, right? We'll just call that a. And I know that whatever that vector is going to be perpendicular to n, right? That's just the definition of the cross product. So once I have a vector that's perpendicular to n in that way, I can then say, let's just call that vector the x-axis, right? So I can say any vector cross n, I could call that the x-axis. I just have to normalize it, right? Then once I have the x-axis, well, I know that if I take the x-axis cross the z-axis, I'll get the negative y-axis, right? So negative x cross n is going to equal to the y-axis, right? So in theory, if I just do enough cross products here, I will get the thing I eventually wanted, right? I can just keep crossing these vectors until I generate an axis system that's one I can use, right? It's a pretty straightforward concept. It's just a little tricky to wrap your head around when you think about why you can sort of magically take one vector and turn it into a full coordinate system just by repeatedly crossing it over and over and over again, right? But hey, that's just how that works. So we should be able to do something like take a fictitious vector, whatever it is, and like I said, so we just need a way of figuring out what that is. So if we have our normal, what we want to avoid, like we could just pick any arbitrary vector. We could just say it's always the z-axis, right? And then when we cross it, I don't know where maybe the z-axis is going this direction relative to the normal or something. We'd cross it, we'd get a vector out in the plane, we'd call that x, we'd then cross it to get y, and then we'd be done or whatever, right? However, the problem with this idea is that what if the vector that we're trying to start with, the n vector, is very close to this to begin with, right? If that's the case, then the cross product will degenerate, because since the cross product is proportional to the sign between the angles, if the angle comes down to 0, the sign goes to 0, which means that we degenerate and lose the ability to take the cross product at all. We get a 0 vector back. So what we actually need to do is take a look at n and see perhaps whether or not it has a high z value, right? For example, what we could do is say, well, let's say if the z value is higher than 0.8 in here, then we'll use the y-axis. Otherwise, we'll use the z-axis. Or maybe we'll just scan for whichever the lowest one is, and we'll use that one, right? So what we can do with that is just say, like, all right, let's take a look at which one of these would be the best. So let's say we have if n.x is less than n.y, then if n.z is less than n.x, and in this case we'd have y. So you can see all I'm doing here is just creating a thing that figures out which one of these is minimum. And so what I'll do is I'll say min element. And what we'll do is say, all right, if nx is less than ny, then we know that ny cannot be the maximum, the minimum element. So then we just have to go, well, is it nz? If it is, then the minimum element is the second element, is z. Otherwise, it's x, right? And the same thing would hold true here, but the only difference is the minimum element. The minimum element would become 1 instead, because it's y is the minimum now, not x, since we've determined that y is actually less, right? So if we do this, we can then say, all right, let's take our base vector here, which is all zeros. We'll then set the minimum element of whichever one the normal has at a minimum. We'll set that to 1. So we're basically picking the cardinal basis that happens to most be as far away in terms of magnitude, in terms of direction from the normal. And then we just start crossing. So first to get our x-axis, right, in this case we want to cross. It doesn't matter which direction we cross them really, because again we don't have any other definition of this coordinate system other than it's got to not be n. It's got to not have any component in n. So what I can do is, all right, let's cross it. First we'll cross the base with the normal. That'll give us our x-axis. Then we'll cross the x-axis with the normal again. And like I said, that's actually going to give us the negative y. It doesn't really matter, again, because for our purposes we don't care, but we just want it to be wound properly. So we want to negate that so that it's going to be the positive y. And again, that's just so we'll produce a proper winding. So once we have these two, we basically want to normalize. And we want to multiply by the radius, right? Whatever that radius is going to be. Or we could do that here, right? But we might as well do it, bake them into the x and y axes. So if we take the element radius and we put those in here, then we've, again, just got a pretty straightforward process to create the diamond, and off we go. Got to grab that n from somewhere. And these are v3s. So actually, we just want to do Yeah, so we probably don't want to change the z-bias in this case, which makes it a little bit tricky because we factored the z-bias in already. So the z-bias value is going to be kind of erroneous, which is unfortunate, but that's just the way it is, I guess, in this case. Oops. So I think what I would like to do here is just zero out the z-bias. So we're just looking at the actual reflectors themselves. All right. Not great. Not a very auspicious start, if we're being honest about it. But that's basically what we're looking at here, right? So let's take a look here. Yeah, let's first just get rid of the positional part of things. All right, so we've got first a problem with color, which is sort of separate from the positional, debugging the positional creation. So in order to compute the lighting here, where we create the front emit C and take the ref C, for some reason we're not properly passing through the color. Which is odd, right? Because what should be happening here is, right, we get the elements from the quad index here. And each time we should be passing, taking whatever that color when we unpack the color of the first vertex, which should always be proper, something, fairly bright. We're taking the RGB of that and we're putting that into the reference color. We're then copying the reference color into the front emit color for each individual element, right? We loop over them all. And this is just pretending we actually did some lighting. We didn't. We're just taking the reflected color and pretending that that's what you actually see coming off of the surface. However, that should basically reconstruct whatever the reflected color was, or this thing that we unpacked from vertex 0. So then when we go to copy it back in here, where we do our front emit 32, we set the colors for each of those to that. When we go to pack it, we're taking the front emit color, which again we should have taken and copied vertex 0's information into there. Right here is where that should have happened. So coming back around, we should end up with this being pretty much correct. I'm not sure what's going on there. So let's go ahead and not do that. Because there are the actual colors. So we're doing something wrong in terms of the copying that out. So let's first take the element front emit C and verify that it's the fact that we're not setting the front emit C properly. So suppose I set that to white. Everything should be white. What is it saying? Term is not evaluated to function. Ooh, whoops. Okay, that's a mistake. I forgot about the fact that these are actually functions that we use. Yeah, that's not great. I admit that. That's not my best idea, if we're honest about that. Not my best idea. Let me go ahead and replace V0 with vert0 here. And then I'll replace V2 with vert2. If only the compiler knew what I meant and not what I said. Wouldn't that be wonderful? Like the artificially intelligent compiler. I can't do that, Dave. All right. So I'm just verifying here that it's okay. So that's what I want to see. So it's not that. It's actually this pack that's problematic here, or the transparency value, right? So something about what we're doing here is bogus, or in here, or whatever else, right? So that's good, because I was like, I don't see how this is possibly messing up. So that's actually quite nice that it's not messing up, potentially. It's actually something different happening here. So let me just go ahead and take a look at what's happening there in the debugger to see what got messed up. Oh, you know what? I know what it is. RGB pack is assumes they're 255s. Yeah. Yep. So you can see here, these are just for packing color values that are non-normalized. We don't have a pack unpack that fixes that, I don't think. Yeah, so we don't really have one of those. So basically what happens here is when we unpack these colors right here, this unpack is not going to divide the colors by 255. So we need to basically do, this, so that we will get back proper 0 to 1 colors. And then when we go to pack them again, we need to do the opposite of that, because they're not going to be based off the 255 properly. Furthermore, here the transparency is not going to be correct either. So we could say, like, to do Casey, remove the pre-multiplied alpha here, if we want to start handling transparency in the reflections as well. So yeah, so right here, what's going to happen is during the front emit, this RGB pack, again, this is going to pack down things that it expects to be in the 255 range. So it would need to multiply that out again in order to get the 0 to 255 values. Now, since they're clamped, oh, no, they're rounded, so that's fine. That's probably fine for our purposes, at least at the moment. All right, getting a little closer, but still not there yet. So when let me go ahead and again take the front emit C out of the equation there, and yeah, perfect. So looks like this is correct now, but it looks like this one isn't. So when we unpack the color, should be 0 to 255. So I assume that that's correct. Let me just double check that. Yeah, so these would come out 0 to 255 for sure. So I feel like that's correct. Let me again take a quick look at that code. I want to see what I'm getting there. All right, so what I'm going to do is I'm going to look at vert 0 here, and I'm going to look at the color. See the color there. And then I'm going to look at what the element's reflected color is computed to be. Um, and that looks roughly correct, right? I don't actually want to stop there anymore. You see a lot of those are quite reasonable. They're exactly what we would expect to see. So all of that looks pretty reasonable to me. Let's go through here and see what starts happening when we set these front emission colors. I'm going to go ahead and look at the elements array. Typo. There we go. And now I think we should be good to go. All right. All right, so now we need to actually get the rest of this working with our positional information. So the next step is to fix that, right? So you can see we don't have our position stuff coming in correctly here. So let's step through this and see what we've got and try to make this part reasonable. So I'm going to go ahead and step in here just to see what sort of values we are ending up with, just to get a hint of what we're looking at. So it looks like that's another typo. I'm not very awake this morning, am I? There's just a lot of typos in here. Try that one more time. That's not looking great. So these should not be zeroed out. So what's going on with that? My base vector and my normal. This looks like I did this totally wrong here. So let's figure out what's going on here. So we've got our normal vector. Our normal vector is 0, -1. That's my problem. I forgot these need to be absolute valued, right? Because they could still be negative, which is not at all what we want. So I actually need the magnitude of each of these. Yeah, so what I want to do there is I want to have a way of saying probably something like this. And that way I will know definitively which one is the minimum magnitude, not minimum value, because those aren't the same, right? Okay, and so then this can still use the vertex end in that case. And I think we're all good. And now we'll see how we're doing on values. All right. So those are looking nice. That looks like roughly what I would expect. Let's see how we're doing here. All right, so close, but no cigar. So I guess I don't remember which way we decided to make our quads go. I think it's probably a case that we have them. Let's take a look at push quad here. Yeah, so it's 3, 0, 2, 1. So basically, the way that we've got it here is assuming that it's a wound quad, but this is a tri-strip, basically, right? Is how we're outputting them. So in order to output those correctly, what we need to do is we need to do it in that order, right? We need to do 3 0, 3 0 2 1 instead of 0 1 2 3. So if we want to do it that way, that's not such a big deal, right? Like here's 3, here's 0, there's 2, there's 1. So that's the actual order then, I guess, that it would expect to be shown in. And there's our little diamond reflectors. And they're looking pretty accurate to me, I guess. It's a little hard to say in some of these, but let's go ahead and spin the camera around and see what we think. So here's the world, ostensibly. I don't know what those giant pink ones are. I think those might be the bounding boxes, which we'll probably have to make sure we remove from this. So it looks like we're not quite correct here, though, because, like, for example, if you take a look at these cubes, no, actually, you know what? That does look correct, because the cubes are not square, so that part's all right. So that does look roughly correct to me. These giant pink reflectors are a problem, and we kind of need to make sure that those aren't in there when we're doing the lighting testing, right? The problem with those is, where those are coming from. Let me just nerf out the copy out so we can see what that is. So if you take a look here, let me zoom out. You can see that there's that pink sort of band that just shows like the simulation region bounds. It's a piece of debug information. And the same is true of the yellow square there. So in both cases, those are going to be long, thin rectangles. That makes it appear like they have an extremely large, radius. But the radius isn't actually that large, right? We wouldn't really want to represent it by a giant reflector like that. So it's unclear exactly how we would handle that case. We don't really have to because it's debug, but you can see that that's a little bit of an issue. One thing that we could do here is we could set up a little bit of a guard for that. We could say, all right, let's grab vertex 1 out as well and compute it. We could do say, all right, let's take a look at those two. So there's a check span here where we take both of these. So we get that span out. Let's put the color stuff in a different location. So when we're computing the position and the radius here, what we could do is say, all right, let's look at this check, whatever that check is, and say that whatever the side length is, as opposed to the diagonal, maybe we just say that, you can't be more than twice the side length, or something like this. So we would know, going from 0 to 1 is one side of the quadrilateral. Going from 0 to 3 would be the other one. Maybe we take those two and average them or something like that. In fact, that seems like, or take whichever the smaller of the two is as the reflector or something like that. That seems like a better plan maybe to avoid the eccentricity. I could do that. Let's try that. So what this would be here is I've got, two different versions of the span, and what I can do there is just say, look, whatever the to find the center, I'll just go halfway on each of them. Is that as good? I don't know if that's as good as having the other one, so maybe I should still do all of them. Can't hurt, I suppose. Again, we're not super trying to be efficient here. We're just trying to play with the problem, if that makes sense. So yeah, I can do span 2, 0 for it, but then maybe when we actually compute the radius, what we'll say is we'll take whichever one is the minimum of the two sides. So we'll look at 30, 0, and 1, 0 as the two sides of the quadrilateral emanating from the base vertex, and we'll take whichever one is the lesser of the two. Oops, gotta put in the copy. Out. So here we go. Now we're not using that span 2, 0 for anything other than the placement of the center. And you can kind of see what that amounts to. So, there's the trees and the ground and all that, right? Now, for some reason, we're still getting large. I don't know why we'd be getting such large comparisons there, because at least in theory, I feel like half of the side length, if we're taking the smallest side length, there should be no way for the thing to be there should be no way for it to be that long. You know what I'm saying to you? There shouldn't be. You shouldn't be able to produce producing something so long as that. At least not if this radius is to be believed. This should never be something quite so huge as that. I mean, that thing looked like 20 meters or something like this in the world, which is way more than it should be. So if we're looking for the minimum of those two, of the 3 to 0 and the 0 to 1, I don't see how you get that. Oh, this is me being stupid again. It's because the winding order of these vertices is not that order. Remember, they go 0, 1, 2, 3, so they're in exactly the wrong order. So they would have to go 0, 1, 3, 2 is actually how they would be wound if we actually wanted to put them in correct winding order. Don't know how much of a difference that would make, but yeah, there we go. So that fixes it. And so then you just get these little tiny reflectors in for the debug thing, which is what I would actually want. All right, yeah. That whole winding thing is annoying, and that's just because of the way we sort of hacked the output of those, but all right. So there's some interesting things about this that you can sort of see already, which is that, if you imagine these things were actually disks, which they're not at the moment, But you can kind of see how that's not the greatest approximation for what's happening in terms of bouncing the lighting around. Because whenever you have like long and skinny things, you sort of end up with that problem of not really having sufficient coverage, right? Like you'd want a bigger lighting element there. Now, maybe we can eventually expand our notion of how these things work to be more about quads and less about disks. But at the moment, since we were kind of taking a look at basing what we were doing a little bit off of the old disk lighting transfer stuff, for now it makes some sense for us to do it as disks just to see if we can get that working a little bit better. But again, yeah, I don't know how plausible that's really going to be. And we could always make them a little bit larger in terms of reflectors, how big they should be. Again, I don't know. Stretch it. All right. I don't know how much time we got here. We end in, 25 minutes, I guess? Something like this. Yeah. So, from here, now what I'd like to do is I would like to figure out one of these ones we can use as an emitter. As a test emitter. So let's randomly try to pick the hero. I don't know that we are going to be able to do that. Trying to think of how we do that. We're specifying a lighting as sort of a constant position. We don't really have a way of doing that here. I guess what I could do is add a synthetic lighting element onto the end of the lighting element array. So one way of doing that would be to say, all right, suppose there's an element count, and the element count is actually going to be the quad count. But it's going to be the quad count plus 1. And then what we'll do from there is we'll say that there'll be a synthetic element that we'll use that'll have that lighting information in it. So we've got the current quads, right? We've got the sort of last setup information, and the render setup has the debug light in it, this debug light P right here. So what we could do is use that debug light P to create a synthetic one of these that's just our light source, and we can move the light source around. So what we can do there is say, yeah, like all of these, we're not going to do this emission thing anymore. When I run this, right, you can see that we don't have any of these lit at all. And so then what we could do is we could say that there's a synthetic light source in here. I guess maybe I don't even have to do it that way. I could just use the debug light P temporarily as some kind of an approximation. Oh, you know what I'll do? Here's what I'll do. I'll take the distance to it. So I'll say, all right, your front emit is 0. However, we'll basically say that if the distance between you what's your position, right? So this element's position minus the debug light P. If the length of that is less than 1 meter, then you're gonna be lit. And so all we have to do there is use that render setup to get some kind of a debug light P in there. So I believe all we have to do is just say last setup debug light P. I think that's all there is to it. So now, in theory, we should be able to tweak that somehow to figure out how to light some things up while keeping other things unlit. There we go. So now we sort of are preceding those emitters, right? Those particular lighting elements that we have are now lit, right? They are artificially pushing light out into the world. So let's suppose we've got these things here, and now we're just going to be stupid. We're just going to be just dumb and stupid. So if we wanted to do a basic lighting calculation to prove that this was working at all, again, we can go ahead and do sort of our basic lighting. Let's turn this into an n squared loop, because why not? So I'm going to have two of these here. And then I'm just going to do an n squared propagation of the light, which is going to be a disaster, right? But that's okay. I don't mind it being a disaster at all. Again, I'm just playing around with this. And we can also limit the number of stuff in our, like reduce the amount of stuff that's in the scene to take it down from 2000 and put it into maybe the 100 range. In fact, I could do that right now. Maybe I will. And so what we're going to do here is just say, like, all right, I've got a source and a destination. I'm just going to compute the lighting transfer between them. So I'm going to say something like, okay, so, you know, the thing we were doing before, where we were trying to do the light transport here. Here we go. So let's see. So, you know, we've got a thing that's the direction to the light. Well, we know how to get to the light source. That would just be the source's position minus the destination position. That's going to go to the light source. We've got the reflection normal. In this case, is just going to be our normal, right? So the destination's normal. The diffuse coefficient, the specular coefficient, we don't know yet. So let's just assume that these surfaces are fully diffuse at the moment. And the specular power is just going to be some other thing here. We'll take the diffuse inner. Do we have POW? We don't have POW yet. So that's a little bit of a problem, but all right. So the diffuse inner product is just going to be exactly what this says it's going to be, right? So all of this stuff is pretty much exactly what you would expect. The light color in this case is just the dest frontimit. Yeah, and I think that's basically it. And so whatever the result is here that we're going to get, in this case we have the reflected color times the total incoming light is going to be the result. So we'll just take whatever the destinations frontimit is, and we'll add the result. So this is just accumulating light into it, right? Test index, source index. Now this is not a good loop because it's gonna propagate light in a, yeah, we'll talk about that in a second. There's issues there. So in this case, we've just got a Handmade product. And the same is true here. But it seems unhappy. Why are you unhappy with that? We've got diffuse color. Oh. Because actually you wanted to do that. And so the vector to the camera, that's not something we have actually determined. So we need in our debug setup, I guess we do have a camera position. So we should be able to do something like camera P equals group last setup camera P. Do we have that? Yes. So when it needs to camera, we should be able to say where the camera is relative to this. To camera is just going to be camera P minus dest P. Right? So again, this is just a complete, this is just completely crappy, and it'll be extremely slow, or it won't stop at all for some reason. I don't know what was going on there. That should be okay though, right? Why are you going so slowly? Did I miss a... Well, that's incredibly slow. That's much slower than I would have expected, actually. Where's my hexadecimal? There it is. So let's see. So we have 2182 times 2182. To be fair, that is 4 million elements it has to do, and there's a lot of instructions here. So I guess it's not that surprising. So what I'd like to do is I'd like to cut that down to a very small number just so we can play with it a little bit better. And so in order to do that, what I'm going to do in world mode is I'm going to take the particles out. And then I'm going to, when we create our world here, I'm going to also say, when we do screening index, I'm going to only have one. And I'm going to see what we can get that number down to. So that's still quite high. I would like to know why we're still getting so many things. So I would, I'm just gonna go ahead and see what I can see here. So here's all of the stuff we're sending down. Now the room is much too large, I guess is one of the things. I don't know if maybe I can reduce the size of this room somewhat. When we do add standard room, room radius X and room radius Y. I guess I could force the room radius X to be smaller. But that still seems like, yeah, I guess we could make it even smaller still. If I wanted to, I could say, something like this. And there's like a pretty tiny one. Now, I don't know, like I said, how many of these things we're drawing now. It still seems like an awful lot of quads. 500 of them? Like, where are they all? Is that really right? I mean, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, I guess I could say we know there's at least 6 for each of those. Yeah, so I suppose there's just a lot if you've got 6 for every cube. So, n squared is still going to be pretty rough on this guy. I admit that. But we'll see what we can do. So there it's like, you know, barely running, but it is running. And we could, if we wanted to, also potentially look at if the optimizer can make that loop run faster, because since all the time is going to be spent in that loop now, yeah, there it goes. I don't know why I'm getting that flickering there. Are there multiple quads stacked on top of each other? But anyway, so if we take a look at this here, this is probably cheating because it probably figured out that this loop can go away, and that's probably why it's fast. So let's take that away and make it actually do the work and see what it's like if it's optimized. Oh, that's not too bad, actually. All right. All right, so let's try to get this working here to something that does some kind of light transport. So what was it doing? It does source P. Yeah, the light color is from whatever. No, this is wrong. Here we go. Try that one more time. All right. Well, that is interesting, to say the least. In this case, we're going to have to clamp when we push this information down. Otherwise, we're going to get all kinds of weird stuff like that. So we do need that clamping to come back into play here. So when we do this summation, what we would need is back when we do our copy out and we do our pack, we need to take our front emit here, and we need to clamp each of the components from 0 to 1. Because after we've done the lighting sort of transmission, we got to clamp it down. So if we're going to do something like that, we need to say, okay, so clamp 0 to 1, whatever the element's front emit C is. Oops. And that'll produce a front emit that we can then pass through here that should be properly clamped. So we won't get those weird like color wrapping artifacts where you go over 1 and wrap back around to 0, which is what was creating that flickering, right? So yeah, still have some weirdness here though. I don't know why we're getting some of the things I'm seeing there. So, like I said, this loop's a little bit weird, and the reason that this loop's a little bit weird is because when it computes the lighting, it's going through all of the sources, which include sources from behind, like ones that have already had the light transferred. So we might want to say something like, well, yeah, I'm not sure exactly how we would say that. We could use a different accumulator. So for example, we could do something like, we could accumulate into the back emit C and then use the back emit C or something like this. Or for now, just to make things easier on ourselves, I guess the other thing I could do is just use a separate light accumulator. So basically in here we would say, here's the lighting element. There's an accumulated light field here. And what we do is we just sum in that. So when we initialize these originally, we assume that no lighting has been accumulated. We accumulate the light like this so that we can distinguish it. Excuse me. Why is my little head thing gone? Well, I don't know why. If this is where my head is here, I don't know where the little head thing went. I think Windows just always seems to be very bad at keeping on top windows actually on top, unfortunately. But anyway, point being, then in here I'll just use the accum C, and that way it's not doing. The problem I was worried about is that as we were propagating the light around, later people, as they loop over the source, would pick up that lighting. Yeah, and there you can see that sort of helped out that problem a little bit. But it still seems wrong. It still seems somewhat incorrect. I'm not sure what we're seeing there. So here's the rest of the computations. Let's just take a quick look. Yeah, so a couple things about this. So one, this still has the angular element to it, which we sort of were saying was probably problematic. However, still should be okay. So if we take a look at what's going on here, we say, all right, we've got the destination one that we're going to be summing into, and we've got the source one that we're going to be pulling from. We grab the light color from the source. We grab the direction to the light by subtracting these two. Do we need to normalize that? That's the problem. Yeah, this is assuming this is normalized. Where's the distance to the light? So it looks like we kind of got rid of a lot of important stuff in here. All right, so let's fix that. So we've got two light. Let's do light distance. So let's restore the way this computation was working before. So let's take a look at the light distance. We'll look to see if it's greater than 0. And then assuming it is, we'll normalize and continue, right? I guess 2 camera is the same way here. So once we have the camera information and the lighting information normalized, then we're in better shape. However, you notice we don't seem to have lighting fall off in here anywhere. I guess because we were just hacking around with it before. So we need that to be in here as well, and it's currently not. It was just angular fall off was the only thing that we were computing, which is totally wrong. And at least now that's normalized, which is, I guess, good, but again, it's still a little bit wonky. So let's see what we got here. So we have the 2 light here, the light distance. 2 light is then normalized by multiplying by 1 over the distance, which is good. we've got the reflected normal, which is this one. We compute the inner product of the light and the reflected normal. That seems good as well. No issues there. Yeah, that all seems good. It just needs a distance space fall off. So then we've got the reflection vector. That all seems good. The inner product of the specular, that seems good as well. Yeah, so that all seems good. And the specular isn't contributing at all right now. It should be 0, so that should be fine. So that all looks good. So yeah, I'm not sure why. I still don't understand what I'm looking at there. That doesn't look right to me. Like if you look at what's happening here, you can kind of see that. Well, I guess, that's probably just the angular fall off. I guess I could believe that since we have no distance fall off at the moment. I guess I could maybe sort of believe that, but not really. But anyway, so if that's the angular fall off term, even if I convince myself that that's correct, which I'm not really sure it is, let's go ahead and put the distance term in there as well, which is just going to be like, so that's just going to be, again, inverse square law. So that would be 1 over the light distance squared. And in here where we're actually sort of summing up all the rest of these things, we'd just put in the distance fall off there. So now at least we're getting that distance fall off, but I feel like maybe there's a little bit too much of an angular, like the amount of angular flickering we're getting there seems a little odd to me. It just doesn't make a whole lot of sense. I mean, it does seem basically correct angular-wise, meaning, the stuff that's down here is getting no light, and the stuff that's up here is getting light, and that makes a little bit of sense, I guess. On the other hand, part of it doesn't really make a whole lot of sense because, well, I guess we're not using the other light's facing direction. So I guess that part's okay. I could convince myself that was roughly right. All right, so you can kind of see that this is sort of working a little bit, right? So yeah, so that's like, all right, so there's a little bit of light transport happening there. I think these equations are kind of wrong. Tomorrow I'd like to go through them and actually start to try to tighten this down a little bit. But the other thing we can do here is we could say, well, we could also do this as a multipass operation now and see what happens if we just let the light bounce a little bit by doing a loop. Again, since we're already very slow and this is a problem, this is not great, but we're just playing around. So let's suppose I allowed this to do 3 loops. And what I did here was I just said, like, all right, just propagate the light out. And each time you propagate the light out, assume that you then take the emission and you take however much light you accumulated, and now you're going to shine that light back out, right? So again, just a lot of really weird flickering there. So I think we've got some bugs that we could probably fix without too much trouble. But again, we're getting there, and this is a much saner way for us to do experimentation here. Because at least with this system, I can see everything, and we can play with stuff quickly, and we can do whatever we want, and then that way we don't waste time with a bunch of GPU nonsense when we don't really know exactly what we want. So yeah, I think that's definitely helpful, I would say. Um, so again, I'm just not sure. I feel like we're getting some odd behavior here. And if I take the distance fall off out of the mix, right, and we just look at one sort of pass here. Let me also drop the iteration number down. Like, I just don't understand why the lateral moves are creating so much flickering. It's like it's passing through some sort of a it just doesn't seem like the amount of motion should be able to create such a difference in terms of the angle change between so many different things there. So when I look at this, I'm just think we've got a bug in here that maybe I shouldn't be looking for right now because we should wait for tomorrow to look for it. But otherwise, that's my thinking on it anyway. And again, there's not a whole lot happening here. Like basically, it just takes the inner product of the vector from the light, the vector from the place we're trying to compute lighting to the light source, and then the normal of the surface. That's the only thing we're taking here. We then do the product of the diffuse fall-off, which we've removed, the diffuse coefficient, which is just 1. So those are non-terms. So it's just the cosine of the angle times the incoming light color, right? That's all we're doing. And so somehow that cosine angle term is really getting pretty jacked in terms of its fluctuation. And I just don't know where that's coming from. Now, it's possible, I guess, that something else is kicking in here, but in theory, the specular coefficient, since it's 0, should nuke out anything else that we're getting here. And so we should just be looking at really nothing other than just a diffuse inner product that should be smoothly varying. Like it shouldn't be that drastic, but maybe it is. So yeah, I guess that's all there is to that. So let's go to the Q&A here. Yeah, I can't enable the overlay. It died. The problem with that is that for some reason Windows just sometimes removes it. Like, as far as I can tell, nothing is happening weird in C-Tray. It just removes my overlay. I do not know why. Just Windows being Windows, I guess. I should try and figure that out, because it happens every so often. So is it gone? I mean, is it actually totally gone? It's crazy how many windows are open. So what are the styles of this window? Pop-up, visible, clip, siblings. So you can see this is a topmost window that's visible. It is a topmost visible window. Its coordinates are exactly the bottom corner of the screen. Right? Where is it? Like, where is it? Anyone? Someone want to tell me where it is? I have no idea. But it sure does appear to be there. Yeah, I don't know. Martin's Mosaico says, sorry the trick didn't work. It works for the editor I use. Yeah, the thing is, I suppose 4Coder is a little too smart. Is it like it actually parsed the C++ as C++'s grammar says to, which is, in most cases, I guess, is what you want. In this case, it was too smart for us, right? Because we were hoping it would be dumber about the string. But, hey, Martin says, there is an option to try to use old non-raw string literals. Char star shader equals stringify parentheses, write multi-line code here, close parentheses, where stringify is a macro with pound preprocessor thing. Compiler will smush multi-line code into one line string and you'll lose line numbers and error messages, but they don't seem to be used on stream anyway. That's interesting. I've never tried that. Does that work? So basically what you're suggesting is to do something like this. Is this what you mean, Martins? So we would just say, because I would assume that's not going to really work, because also you wouldn't be able to really close parentheses in there, would you? I feel like. I guess the other problem is, too, I feel like that doesn't work because 4Coder's, again, too smart. It knows that brackets couldn't be done in here that way, I think, maybe? No, maybe it's not. So yeah, that I guess would work, but what about having quotes in there? I guess is my only question. Like that probably works. But I'm a little nervous about if there's quotes. Now maybe we don't use quotes ever in the shaders, so maybe it's fine. In fact, I guess they probably wouldn't. So that is, maybe that's their best, maybe that's the best option. So let's see. It's weird that that doesn't indent properly. I think that's a fork-order bug. Maybe it's already been fixed. But for some reason, if you block indent something like that, the first time through when I did it here, it wouldn't indent. But then it obviously can indent it, because if I go through and re-indent it again, it worked. So I don't know what's going on there exactly. So there's shader code. Down we go. Doesn't look like it understood the ending of this, though. Looks like that's a bug in the indentor, right? Because it thinks that that is there. For some reason, it can't handle what's happening here. In fact, it seems even more confused, I guess maybe because of it's the second one in, it indented it further this time. So I think we just need to ask Alan, because even this doesn't really seem to work, right? The cryptic mind, I do think that it does get addressed a little further down. I think we get rid of the sleep because it was too unpredictable on different platforms, exactly as you discovered. Did the black overlay disappear during the stream or during the Q&A? During the stream, I think, but I'm not sure. From the code, if target active, you could always check the video when I post it. I suppose we will see. If the countdown has finished and whatnot, then it is not active anymore. All right, well anyway, I'm gonna wind it down here. Yeah, we should try and figure out if we can get Alan to maybe put something in here that would work. I'm gonna back that change out for now because it looks like none of those options work. And we can just ask him like what we should do. Like what's the right solution there? Because it's nice to be able to embed code from into a C file. It would be nice if there was some way to make that indentation work okay, right? Martin says you can do char star shader equals shader code parentheses return pound include shader.h, return close parentheses, and then put code in the new shader.h file. Maybe then indentation will be fine afterwards. Wait, but Martins, how would that work? Because wouldn't that take the pound include and stringize it? Martin says, no, that will work. Interesting. I didn't know that you could do that. That's an interesting trick. Martins is saying that you could actually if you do like what I had before, if you do that, he was saying you could actually do this. Which is crazy, because I just assumed that the string eyes would take precedence over the pound include, but I guess the pound include comes first. If that's the case, then the pound include would allow us to just put it in a separate file. And that's probably fine, I would assume. So that might be a reasonable thing to do, because that would also put the shaders in separate files. I'm not sure I'm necessarily psyched about having quite so many files as that would require, but I'm not averse to it. Like, so we've got a bunch of files. That seems okay. Furthermore, if we wanted to be weird about it, in theory, we could actually just glom all the shader code into one file as different functions, and then just have our actual code here just call whichever function it actually wants for that particular shader. Or something weird like that. But that probably would create some problems for the compiler. All right, I'm going to close it down. But that's an interesting trick, Martins. I didn't know you could do that. That seems like it would work. All right, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you'd like to follow along the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can follow along. You can also go to our forums if you have questions you want to ask, our Patreon page if you want to support the video series, our schedule bot if you want to know when we're going to be live, and our episode guide if you would like to catch up on past episodes. That's about it for today. I'll be back tomorrow where we can start playing around with that lighting transport in the CPU side and see if we can't figure out something interesting. Until then, have fun programming, and I'll see you all on the internet. Take it easy, everybody.